Alrighty, I think we're live now. If folks on the live chat can just let me know if they can see and hear me okay. Make sure you can see Mike as well, who's joining us from Vancouver, Washington. And we'll get to him here in a second. Just want to make sure all the AV stuff is up and running, and then we can get started with this. Super excited to have everyone here. Thank you for joining us. Thanks as always to Amanda, Joe, and Susan for moderating the live chat and aggregating all the questions. Super helpful. Looks like we are good to go. And so, yeah, thank you for everyone for joining us. Want to especially welcome Dr. Mike Poland, who is with the USGS and the Scientist-in-Charge at the Yellowstone Volcano Observatory. Kind of a mouthful, but that's what you get when you're at such high accolades. So welcome, Mike. Thanks for joining us.
Yeah, my pleasure. Thanks for having me again.
Yeah, and I actually looked this up because I think this is pretty true, but you're our first 3-time guest. So, I've interviewed a lot of different people doing this over the last couple of years, and you're the one that always comes to my mind when I'm like, gosh, I just want to get a better explanation of this. And so just, first of all, thanks for being a frequent guest and coming on more than once and giving us your time. You're a great communicator of science, and we appreciate it.
Oh, thanks. That's funny. I for a second I flashed to an old SNL skit where they had back then it was like the 5-timers club. And it was like Steve Martin and
yes,
Tom Hanks.
Like how many people had hosted the SNL? Yeah. Well, you're the only member of the 3-timers club on the not so popular Shawn Willsey live stream thing. So I don't know if there's a set of steak knives or what exciting gift we have, but yeah, maybe we're just more bored than anything else, but we appreciate it. So thanks for joining us.
Thanks for having me.
Yeah, and just kind of as an outline, folks, what I thought we would do is let Mike and I chat for maybe half an hour or so. I have some topics that I think people will be interested in, some things we've certainly been watching through the lens of my channel, and some of the things I've been curious about, both in Hawaii and in Iceland. We can talk about anything that's been going on in Yellowstone as well. Some of the volcano monitoring tools that we use. The first episode we did with Mike was kind of getting to know him and his background and his career. Then I think the second one was mostly lots of question and answer. And so we're kind of doing the same thing. I think each time we come back to the Mike Poland well, we're just trying to draw a little bit more knowledge and information and just get his insights, because he's, again, just a good communicator and a wealth of knowledge. So maybe Mike, just starting out with, so I think we've all are familiar with these things called interferograms, which is a ground deformation tool that allows us to see what the ground is doing. It is another method in addition to GPS station measurements, which measure 3-dimensional motion. And they're these psychedelic, colorful looking graphics. And I think I understand them, and I think I can understand them enough to explain them to someone. But the more I kind of dig into them, the more I think I get a little bit more confused. So maybe I can pull up one if you want to see one, or maybe you can just talk us through how they're generated and how you would describe those.
Yeah, if you want to pull one up, I can describe it a little bit, and then we can talk about maybe the one you pull up specifically.
Okay.
This will be a test for me, right, to see whether I can interpret it correctly.
Yeah,
So an interferogram, it's the way to think of this maybe is like a deformation camera in space, although you can also put them on airplanes, and there are ground-based units as well. But the most common application is from satellites. With every radar, typically when you see radar images, you're looking at a backscatter image. That's basically the strength of the returned signal. And in radar images of the Earth's surface, that backscatter is mostly dominated by things like the surface roughness, water content of the ground, things like that. So on a volcano, a very rough surface, like an flow with really a lot of clinkers and versus say like a Pahoehoe flow, which is very smooth, the surface would look bright and the Pahoehoe surface would look darker. Water looks incredibly dark unless it's really choppy. And that all has to do with the amount of energy that sort of bounces back to the radar from the surface. That's the amplitude. That's the strength of the reflected signal. There's another aspect to radar imagery, and that's the phase. And that has something to do with the distance between the radar and the target, the ground in this case, between the satellite and the ground. Now, if you looked at a phase image, it would look like nothing. It would look like TV snow for for those of you that might be old enough to remember what that is.
Just like pixelated, right? Like, yeah.
Yeah, just
Okay.
lots of weird colored pixels. But the phase is consistent over time if the ground isn't moving. And so if you have like an area where the ground isn't moving at all, then the phase actually will make sense when you compare time one image, an image that was acquired at time one versus an image that was acquired at time two, a month later, a year later, whatever. If the ground is moving, then the phase will vary because the distance between the satellite and the ground is changing. And that gets represented by these colorful fringes. Now, we don't know the exact distance between the satellite and the ground, but what we see are basically changes in that distance. And so we're getting a sense of the relative deformation. So you can look at some area of the interferogram, which is the phase difference image, and where there's not a lot of color variability, that's probably somewhat stable. And as you move into areas with a lot of fringes, those are areas that are unstable. And basically, by knowing something about the characteristics of the satellite, the wavelength of the radar image, you can figure out what the deformation is. And the way you do that is by counting fringes. So for example, one of the most common satellites used for INSAR right now is called Sentinel. It's run by the European Space Agency. And the wavelength of the signal there in an interferogram is about 2.8 centimeters. So it means every time you go through a cycle of color, it depends on, every color map can be different, but let's say you're going from red to yellow to green to blue to red to yellow to green. Every time you go through one cycle, that's 2.8 centimeters. And so if you were going across an image and you saw all of these cycles, you would say, count how many times red recurs. And then multiply that by 2.8, you get a sense of the deformation. The actual deformation, whether it's going towards the satellite or away, you have to look at the pattern of colors.
Okay.
Is it going red, yellow, green, blue, or is it going red, blue, green, yellow as you're moving across it? And that will tell you whether the ground is moving towards the satellite or away. And there's usually a color bar somewhere in the image that'll tell you.
That lets you know, right?
Interpret that. And then finally, this is not uplift or subsidence. It's not vertical. It's not north-south. It's not east-west. It's sort of a mix of things because the radars don't look straight down. They look at an angle to the ground. So you're seeing a mix of vertical and horizontal motion in an interferogram, which makes it somewhat challenging to interpret. So radar interferograms they're complex. They don't work everywhere. Places where there's a lot of motion, like a forest. The radar signal is bouncing off the trees. Sometimes it hits a branch. Sometimes it hits a leaf that was farther down. Those areas, you don't get good phase information, consistent phase information. Same thing on snow and ice. That's changing too fast. And so we don't get good radar interferograms off of vegetated areas and areas with a lot of snow and ice typically.
Is it just the snow and ice, the nature of the snow and ice, or because the snow and ice, the depth is changing, like the distance, like the ground, if it's interpreting the snow as the ground elevation and then it goes over another time and you've melted a bunch of snow, is that the problem, or is it something about the snow and ice?
It's sort of all of the above. Depending on the water content of the snow or ice, then there'll be different ways that the radar signal can penetrate into that. But then there's also just a lot of change happening at the surface. If you have a very, very short time frame between images, you might actually be able to detect those changes. And actually, I saw an example of this just a few days ago. We're working on getting INSAR data for Mount Spur in Alaska. Now, we're not getting great results because it's still pretty wintry up there.
Yeah, covered in snow, right?
There's a lot of snow and ice, but there's glaciers all over the place. And we managed to get satellite acquisitions on consecutive days. And the satellite has to basically be in the same place, same time, same satellite. So that's kind of rare that this happens. But when it does, you can get a 1-day interferogram. You can see the deformation happens over 1 day.
Wow.
And this particular interferogram showed nothing related to Mount Spur, but all the glaciers around Mount Spur lit up. We could see all kinds of amazing motion, tens of centimeters over that day, meters in some cases, of motion of the glaciers. And that motion can be so fast that if you're looking at over a week or something, it just becomes a mess. You can't.
So you're really capturing in that 1 day, bit of data, the downhill movement of the glacier, or you're getting volume loss, like vertical loss.
Well, you could potentially be getting volume loss if the ground is keeping the same shape.
Okay.
So then you'd be seeing it going down.
Right.
Where it gets messed up is whether if the ground really gets jumbled up. So for example, if there's a landslide, you don't get a good coherent signal in your
Right.
interferogram because the landslide messes up the ground, and all of the scatterers, the things on the ground that actually send the signal back to the satellite, they're all messed up.
Right.
And so when there's catastrophic change like that, you don't get a good interferogram. You need to have sort of change that doesn't really impact the properties of the surface. And so that's why inflating volcanoes, deflating volcanoes show up really, really well, as long as they're also not covered in vegetation and snow and ice, which
Right. So it works
a
well in
lot
Hawaii.
of volcanoes are.
It works well in Hawaii, I guess, in like the crater, which is mostly just lava flows and devoid of vegetation. Probably doesn't work as well out on the East Rift Zone where there's a lot more trees. Southwest Rift Zone works better. There's fewer trees. And then Iceland, it works great because there's no trees. It's just moss and rock. And so you've got just the right kind of combination of factors there.
Exactly. In SAR, SAR interferometry, radar interferometry is great in unvegetated environments that are pretty arid. Deserts are awesome.
Right.
They're not as great in tropical areas or snow and ice. And of course, a lot of our volcanoes, take the Pacific Northwest, right? They're forests right up to tree line, and then right at tree line, you get snow and ice that takes you the rest of the way up.
Yeah.
So it's hard to get good interferograms from ice-clad volcanoes in environments with a lot of forests. It's great in places like East Africa, where it's pretty arid and there's not as much vegetation to get in the way.
So the topographic expression of the volcano doesn't matter as much as some of these other factors. If I had a big steep stratovolcano in Iceland or someplace where let's take out no ice, no snow, no trees, but it was steep sided, and we're getting that oblique view off that satellite, it would give us a useful interferogram?
Yeah, for the most part. It can be a challenge if they're really steep, because you can imagine if you're looking at it from the side, there are shadow zones.
Right.
Like you may not be able to see the other side of the volcano depending on sort of the angle that you're looking at.
Right.
So there are problems with sort of the viewing geometry, especially on steep-sided volcanoes. Sometimes, typically a satellite will view it from one direction as it's orbiting from north to south, and then the other orbit comes by south to north, it'll view it from the other side. Sometimes you find the south to north image gives you a much better view of the volcano than the north to south image for whatever reason, because of the geometry of the volcano.
Right.
So it's not a magic solution to mapping deformation. There's a lot of challenges, and you may find that some views are better than others. So it can't be applied evenly everywhere. It does take some experience to sort of be able to interpret these things and to know really what the best viewing geometry is, what the best result is, what the best satellite is, because there's probably about I don't know, maybe 10 satellites up there now that are doing this sort of work, and they all have different characteristics.
But it's a free tool because the satellites are just going around the planet. They're not up there for the express purpose of monitoring volcanoes, right? But they're able to do that if you get a good pass, with a window during a period of time when there's inflation, deflation, then you might luck out and get a good. So a lot of these things have to come into alignment to get to even use this, it seems like, right?
Yeah, there's something that sort of have to come together, and no satellites have ever been launched specifically with the purpose of monitoring volcanoes, but this Sentinel mission from the European Space Agency at least comes kind of close, because the purpose there was to look at the dynamic nature of the Earth environment. And so you can do things with ocean currents and things like that, but Sentinel was designed to have this very wide view so that you could also look at very broad tectonic deformation. Think like the interaction between the Indian subcontinent impacting the Asian continent. So you could do really large scale tectonic studies, as well as looking at volcanoes and landslides and ground subsidence due to groundwater pumping, things like that. So that satellite really was designed to look at the dynamic nature of the environment we're living in.
So you can get an interferogram of the Himalayas that shows the fringes that represents very slow uplift related to the tectonic forces. I didn't know that. That's incredible if that's true.
You can. I mean, it takes a lot of effort to get these data out there, because some of the things that are happening very slowly, you're sort of in competition with time in some ways, in that the more time between two radar images, the more likely all of the surface properties have changed, and you're
Yeah.
not going to get a good result. So what you really want are shorter time span interferograms. That maximizes your signal, your potential signal. But the problem is, if something's happening very slowly, you're not going to see it in a short time.
Yeah.
And so this is where you got to get fancy with some signal processing or some creative ways of merging lots and lots of data sets, so you can be able to pull out the very small scale
Right.
components of what may be happening. And on top of all these other sources of noise, the atmosphere is a problem as well. There's a lot of water vapor in the atmosphere that can slow the signal and make it look like deformation when it's just an atmospheric artifact. This is especially a problem at volcanoes, because many volcanoes, as you just said,
have their own weather
tall and
systems.
pointy.
Yeah.
And they have their own weather. I mean, you've seen lenticular clouds
Yeah.
on some of these things, right? And so volcanoes often look like they have these bullseye fringes around them that make you think, it's inflating or deflating. Turns out it's atmospheric. And that has come up. Some people have posted interferograms on social media, not geophysicists, but sort of random people that have access to these data sets or know where to look for them, and say, oh, look, this particular volcano is inflating.
Right.
And it's an atmospheric artifact. So there's a lot that goes into making these images and interpreting them.
Right.
It's an amazing tool. I mean, it's incredible that we can see the ground moving on a scale of millimeters to centimeters from space.
Right. From an object that's like thousands of miles above the Earth.
And moving really fast.
Yeah.
The technological advancements that make that possible boggle my mind. I can't believe that we're doing it. We've been doing it for decades, and we're getting better and better at it. But it's not a magic. It's not something that's just going to work every time, and you get the image and you know what the answer is. It takes some effort.
So if there was, let's say we pass over Iceland, we'll use Iceland as an example. Hawaii would work too. And then on the second, we get an image and it's actively inflating or deflating. On the second pass, let's say there's a big storm over Iceland, or there's a hurricane that's hitting Hawaii. That second pass, we probably wouldn't get a useful interferogram because of the enhanced water vapor, or it would be pixelated and kind of murky. And is that pretty accurate?
Yeah, you might get a messy image. So for example, let's say there was a big intrusion happening, and on top of that, there was a huge difference in water vapor from time 1 to time 2. You would get everything in that image. You would see fringes related to the dike intrusion, and overprinting that would be perhaps fringes related to all kinds of water vapor effects. Now, there are ways of trying to separate those. So for example, there are weather models that tell you something about the nature of water vapor in the atmosphere, and you could use that to create kind of a filter and try to remove the effect in the atmosphere. Again, not perfect, but you might be able to remove a lot of the nuisance signal and then see the dike intrusion that much more clearly.
Right.
So there are some tricks that can be done. But yeah, when you get an interferogram, there's a lot of things that are contributing to the signal you're seeing.
Well, let me ask one more question, and then I'll pull up one, and you can walk us through it. I think that would be helpful. So with Sentinel-1, do they have, like, let's say it's like, whoa, Iceland is an active place right now. They pass over it once. Can they control the satellite and get it over there quicker? Or is it like you just have to wait for that satellite orbit? The satellite orbits are fixed. They're programmed, and we just got to wait till we're in that window and we get our turn again. Is that how it works?
It's an interesting question, because traditionally that's been the way it happens, that, the satellite orbits are fixed, and to get a repeat, it might be, in the case of a single Sentinel satellite, it's 12 days. When there's 2 satellites in the same orbit, it might be 6 days, because the 2 satellites are doing the same thing.
Right.
TerraSAR-X, which is a German satellite, might be 11 days. Cosmos SkyMed's an Italian satellite system. You might get 1 day. More typically, it's 4, 8, 16 days, something like that. However, the technology is changing. There are more small radar satellites that are being launched, these small sats, you might have heard that phrase. And so there are more satellites in more of these orbits, and it might be possible to get shorter time span images just because you're flooding the zone with satellites. We see that with some private companies that are doing this sort of work. ICEYE, Umbra, Capella come to mind as some of these companies. Some of them are capable of doing interferometry. Some of them just point the satellite wherever they want to point it, and you could get an image every few hours possibly, but you can't do interferometry with those because you're looking for all kinds of different directions. That's still pretty useful though, because some of these really high resolution satellites, you can see in the amplitude images and the strength of the return signal cracks that are opening up,
Wow.
or the ground clearly being disturbed in a way that, INSAR might see, but it's so obvious you can see it. You can see it just from the amplitude images, just from that strength of the backscatter. And an important constraint here, an important capability rather, is that radar can see through clouds and it works at night. So
Yeah.
unlike a visible image where you've got to have, a solar radiation lighting it up, so you got to take the picture in the daytime, and you can't do it when there are clouds. Radar works day, night, any type of weather.
Mm.
So radar really has a lot of advantages for monitoring anything that's really active: landslide, ground subsidence, volcanic activity, earthquake activity, especially from space.
Right. Wow, that's fascinating. Yeah, let me pull this up real quick. I as you talked, I had obviously like 3 or 4 more questions, but I'm like, I think it'd be cool just to have you like walk us through an actual interferogram, and just to, so when people pull these up or see these, they can see. Let's see. Whoops, I got Hawaii up, don't I?
Yeah.
Okay. Well,
that's great. I like Hawaii.
that's the wrong one. So let me go.
I feel like I could interpret an interferogram from Hawaii without too much trouble, but
right,
other places I'm going to have to do some thinking.
Okay, let's strike one. Let's try this again. Let's see.
If you like, I might be able to bring one up.
Oh yeah, give me one more shot, because this one from I'd really like to hear your take on this one from Iceland, if I can.
Oh dear.
Yeah, if I can get it to work. So let's just do this. Let's try this here. Sorry, just give me 1 second. I don't know why I'm having trouble with this. I have it up on a screen, but it's not. All right, let's try it this way.
Beautiful.
How about now? Is it there?
Yeah, that's gorgeous.
Great. Yeah, so this is one from, well, you can see the dates there and such, but this was this intrusion. This might be a good segue anyway into my next set of kind of questions for you. Yeah, just talk us through what you see there.
So many nice signals. So one thing you're looking at is, this is TerraStar X, so this is a German satellite system, and you can see
hold
that
on real quick, Mike. Hold on, Mike. Apparently you can see it, but everyone else can't. So sorry here, team.
Oh, trust me, everyone, it's gorgeous. This is beautiful.
Yeah, well, now you're hyping it too much. Let's see, I can't quite see. Sorry to bug you there. Get that bigger. Okay, I think this will work now. All right. You can still see it, Mike?
I can.
Okay. Everyone else sees it now too, so I think we're good. Go ahead.
Okay, so this is a TerraStar X interferogram from the German satellite system, and you can see the dates: April 3rd, April 14th, separated by 11 days. So that's how long it took the satellite to get back to the same place in space, looking at the same place on Earth. So that's the repeat time. And you have to be able to get an image from the same place in space of the same place on Earth, roughly, in order to make these interferograms. The coherence is great because there's really not much vegetation here. It's a short time span, which really maximizes your ability to get a lot of phase information back. And I can see 2 really interesting signals in this. The first is that really nice big concentric bullseye. And that is a sign, usually when you see these bullseyes, it's a sign of the ground either rising or falling, sort of like as a inflating balloon or a deflating balloon. One thing I can't see on this image, and maybe it's because it's lower than I'm seeing right now, is this color scale. Is there a color scale on that image?
No, when I scroll up and down, it just says wrapped. We
Okay.
can
Well,
maybe
wrapped means the color scale is, so let's pick, for example, the purple fringe, right, on the outside of that big bullseye.
right here. Yep.
I happen to know that Terasar has about I think it's a 1.5 centimeter or so wavelength when you're looking at these interferograms. So that means when you go from purple and then you go in to red, yellow, green, blue to purple again, you have accumulated 1.5 centimeters of deformation.
Right. One
The
wavelength.
scale, if it was there, would tell us whether it was up or down. And so I can't tell you offhand what this is. But then go in again to the next purple fringe, and that's another 1.5 centimeters. So now we're at 3.
Right.
And then you go into the next purple fringe, and that gets us to, so not that one there, but we're looking at the bullseye.
Yeah. Sorry.
Yeah. So if we go into the bullseye, so if I count the fringes from the outer purple into the inner purple of the bullseye, I go 1 fringe, 2, 3, 4. With about 1.5 centimeter wavelength, that's going to be about 6 centimeters of deformation
During that 11-day interval. Yeah.
During that 11 days. And whether it's up or down, we would know that from the color scale.
Right.
Now there's that other little signal that's sort of off to the northeast.
Mm-hmm.
And that one has a different pattern, right? It looks like sort of almost an ear, right? Part of it has these really nice fringes and an oval, and then the other side, it's a little bit less so. That's a pretty characteristic sign of possibly a dike intrusion. And so that's where you have magma rising as sort of a sheet. It may be rising at a bit of an angle. It's being viewed at an angle. You're not looking straight down on it. So you get more deformation on one side of the dike than you do on the other. And again, you can count the fringes. If we go, say, from pick yellow, I suppose, 1, 2, 3, 4 again. So there's probably about 6 centimeters or so of deformation there. But because you're not looking straight down on it, it has kind of a weird geometry. But you can sort of see where the magma is located because it's along that break in the colors.
Mm-hmm.
That goes right down the axis of that kind of earlobe shaped thing.
So you would.
There's a lot of other interesting signals in here that
Yeah.
look like they might be cooling lava flows. These sort of lineations that are sort of just to the south of the earlobe.
Okay, like down in here.
Yeah, I'm not sure if that's what they actually are, but they look like lava flows to me. Lava flows cool, they compact, so they sink. And then there's sort of these scattered bits, especially to the north of the earlobe, look like little puffy clouds.
Right.
They probably are puffy clouds. That's probably atmosphere.
Yeah. So you can tell that just by the geometry that it's probably a puffy cloud versus a land-based feature. You're just kind of using.
Yeah.
Okay.
They're possibly real, but it has a look to it. When you look at enough of these interferograms, you sort of recognize, well, that's probably an atmospheric artifact versus some of these other signals, which look very geophysical, which look like the ground moving.
Okay.
So yeah, look, we've obviously got some really interesting broad feature. That's the big bullseye. You can also tell something about the depth of these. The broader the signal, generally the deeper it is, because the deeper you go, the more ground is impacted by the deformation. So that broad bullseye probably is suggesting a deeper signal than that earlobe feature, which is probably a shallow dike intrusion. And then all of that little messy stuff to the south of the earlobe, I'm not as familiar with the recent eruptions there as I perhaps should be, but I'm guessing those are lava flows that are cooling and sinking.
Well, you have a lot of other volcanoes to keep track of, so we'll forgive you, Mike. That's fine. So let me ask a question about the big bullseye. So is there a relationship between the diameter of the bullseye and the intruding, if these are sills or like the diameter of the actual magma body that's causing the deformation? Is there any sort of like 20-to-1 or some ratio that generally is a good barometer there? Anything that works?
It's sort of debatable because the way we get at the geometry of the systems is to model this deformation. So you can imagine you've got this, let's say it's an inflation signal, and you can decide, all right, I think that this inflation is caused by a sphere that's at some level.
Right.
And you can get a sense of just how much has been added to that sphere. We don't know the absolute volume of it, but we know that the volume change has been a certain amount and what depth and location the sphere is sitting at. Well, you could also produce a similar signal with a sill. And so that sill may sit at a different depth, may have a slightly different volume change to produce the same kind of deformation. So it takes a lot of geological insights to tune your models and know kind of what's the most likely geometry.
Right.
And you can also get data from other viewing angles. So this particular image is based on the little arrow that is at the very top of the image right now. We know the satellite was traveling to the north and it was looking off to the right. There are other views where the satellite's going to be traveling to the south and looking also off to the right, but it'll have sort of the opposing look angle. When you merge those, you might be able to get a better sense of whether or not it's a sphere or a sill or a tabular intrusion like a dike, or it's the dike dipping in some way.
Right.
So
because you're still only getting top-down information. You're really not getting a 3D image of the magma storage system. You're really just getting the top view, which can be interpreted so many different ways. Is that fact?
Yeah, you're seeing what's happening along the radar's line of sight, which is not vertical, not horizontal. It's a mix
oblique,
of the two.
Yeah.
So it gets really weird, and that's why that earlobe feature looks as it does. If we were looking straight down on that, it might look a bit more symmetrical, although it would depend on whether or not the dike were vertical or whether it was tilted.
If it's dipping or not. Interesting.
Yeah.
Okay. Well, that kind of helps a little bit. Just getting. I think that's what a lot of us, myself included, were looking for, was like interferogram 101, like class of just like how to like interpret these things. And you know, I knew the bullseye fringe thing was the easy thing, and that's what we've seen a lot of in Iceland and in Hawaii as well. But I think once you go beyond just a magma storage inflation deflation scenario to like dike intrusions or faulting, even, like it's a totally different sort of beast there. So
it can get super messy when you get faulting, that sort of strike slip with a component of dip slip motion on it, and the patterns of fringes you get can just get really crazy.
Does the USGS or anyone have like a good set of like, here are a bunch of interferograms from different events, and so like someone could kind of go through and see like, here's what normal faulting would look like on an interferogram, here's what strike slip faulting, or here's what a magma large dome intrusion or a dike, like that would be really helpful if something like that was set to.
Yeah, sort of a library. I suspect there are some things like that on, especially there's a group based in the UK called Comet, and they do a lot of work on earthquakes and volcanoes with respect to INSAR. They have a huge number of examples on their website. But I think that might be one of the more likely places you could find sort of a library that you might compare to. There's probably a few other places online. We've done some articles for the Hawaiian Volcano Observatory Volcano Watch series on how to interpret interferograms.
Right.
So there's some examples there. So if you do sort of a search of Volcano Watch and INSAR or interferometry, you'll get some examples of interesting signals that have been picked up in Hawaii.
Right. Okay. Well, that'll be helpful. I think just, you know, for folks like me and others that are just looking to like, well, what would it look like if it was, you know, what if the interpretation was something else? What would that look like? And until you've actually seen it, you don't really know what you're looking for. You're just like, something's moving.
And sometimes it is so chaotic. I'm thinking of back in June of 24, there was an intrusion and eruption into the Southwest Rift Zone at Kilauea. And that caused a bunch of faults to move in the Kauai fault zone. And then there was the dike, and then there was a magma chamber that was deflating at the summit. It is an absolute mess of an interferogram. It is, you can sort of say, all right, well, I know there's a dike intrusion, there are a lot of faults that were moving. But trying to actually, oh man, it is, it's messy. It's fascinating. It's a beautiful image. But trying to understand the source of every single signal, every single offset, that's a nightmare.
What would you use in conjunction with that kind of interferogram to help kind of put, as detectives basically, to kind of put it together? The GPS, I guess you're just looking to see the GPS corroborates the INSAR signal, but then what else would you be looking for to kind of figure out the meaning, the interpretation?
Well, I think generally you want to start with the biggest signal and sort of say like, all right, well, we know back in June of 2024, the big signal in the Southwest Rift Zone is a dike that went from the summit area down, you know, like halfway to the coast.
Right.
And so you sort of try to get that matched with the deformation you see and say, all right, well, we know the dike is at a certain depth, it's a certain length, it's got a certain volume change that varies along the strike.
But the dike parameters are determined more so from the earthquakes, or you think more from the INSAR data? Like
they can be aided by earthquake activity and so forth. But generally what you're trying to do is you're trying to match the signal you see in the INSAR.
Okay.
And so if maybe you get, pretty close to what you think the dike is, and then you can pull that signal out and see what's left over. And say, okay, well, I'm missing a bunch of faulting that happened in this area, and you try to approximate the faulting and then pull that out. Okay, now I'm missing the subsidence at the summit because the magma chamber there deflated as all the magma went down the rift zone.
Yeah.
And so you try to build a model that way, and it is guided by the geology. Maybe geologists were out there mapping cracks so they know where
the
all
structures. Yeah.
It's guided by seismicity. Okay, we know that there was earthquakes this far down the rift zone, and that matches where the deformation goes. So you don't want to throw any of that information away, and you want to make sure that you're incorporating as much of it as possible when you develop this sort of model.
Okay. Well, let me ask you a question about Hawaii. You were just in Hawaii. Let me go ahead and stop the share. But you were in Hawaii a couple weeks ago, you told me, doing some work. And I guess this is a question that pertains both to Hawaii and Iceland, and it's something I don't really understand, and maybe we don't understand it at all, but you can provide your insights here. And that is, so in just this last calendar year in Hawaii, we had eruptions at 3 different locations. We had a small southwest rift zone eruption, a small east rift zone eruption in the Middle East rift zone by Nepal crater, and then we've had all the fun activity up at the summit. And I guess my naive question would be, is that all fed by the same magma storage zone, or are there multiple ones? And then my second question would be, what is controlling you're already laughing at me. What is controlling what's controlling which way it goes? Is it just something like, we had a 4.2 earthquake, and now I sort of envision like the plumbing system changing after any sort of mild to moderate tectonic event or volcanic event, because you're just little shifts, and now that's sending the magma maybe in a different direction.
Yeah, and this is sort of the $64,000 question, right? Like, where's it going to go next? And there are so many variables that go into this. Your magnitude 4 earthquake is one of those variables. The rift zones are constantly opening,
right?
Because the south flank of Kilauea is pulling away from the rest of the island. It's slowly moving towards the sea.
As a function of gravity, right? It's not that the magma's pushing it. It's mainly a gravity. There's no support and structure there. Okay.
Yeah. So it's sort of gravitational failure. It may get some pushes there's some interesting feedbacks that can happen when there's a dike intrusion. We saw an episode back in 2007 where it looked like magma injected into the rift zone, probably because space was being created by that gradual opening. But the magma also then gave kind of a shove to the south flank, which moved a little bit more, which opened more space, which allowed a bigger dike to come in.
Right. It's
feedbacks.
It's like these positive feedback loops, right?
Yeah. So it may be that, the rift zones reach a point at which, all right, it is sort of advantageous for magma to move in that direction because you've sort of released the confining pressure. You've opened the door enough that it's easier for magma to get in there. Once it's in there, it's sort of taken up that space, and now it's not as easy to go in that direction. So you have an eruption at the summit or eruption in the other rift zone. Truth of the matter is, we just don't have enough information of what's going on in the magma chambers, and it is a complex system. There's multiple reservoirs, and it's not just magma, right? It's not just liquid rock. It's a complex, multi-phase mixture of exhaled gases, dissolved gases, liquid rock, crystals that are precipitating out or crystallizing out of this liquid rock. And that makes it all the more complex. The physics of what's going on there are something that we don't have a good handle on, and that stymies us from being able to forecast exactly which direction it's going to go when.
Right.
So that's why monitoring is really so critical to be able to say, all right, now it does look like it's going down the east rift zone, or it's going to stay at the summit.
Yeah.
Because it's very difficult to forecast exactly what's going to happen.
And I think one of our last times together, you told me that, and correct me if I'm wrong, but the earthquakes, no, the ground deformation, you said was the first. But you're a ground deformation guy. But the ground deformation was like the top tier data, and that the earthquakes were supplemental. But you also told me that some geophysicists think of it the opposite way. Have you had any like interesting revelations or discussions on that front?
Well, the reason I think, there's a couple of reasons I think this. One is because I happen to be a deformation person. and I like to tease my seismologist colleagues and
Right.
friends. So, there's sort of a friendly rivalry,
Yes.
but there is a reason behind this. And so, you know, ideally I would do this with a pencil because I'm not going to break this. But, if I were to break this pen, right, the first thing that happens is it bends.
Mm-hmm.
And so the bending is the deformation. The breaking is the earthquake. And so before you can break something, before you can have the earthquake, you got to bend it.
Yeah.
So shouldn't you see deformation before you see earthquakes?
Right.
And in fact, in some places we do. South Sister in Oregon, we could see that inflating aseismically. There's some places in Oregon you could see that inflation happen aseismically, and then the earthquakes come later when you sort of exceed the strength of the rock by that stress you're putting on it from the inflation.
Right.
Um, it's too simple. That model is too simple, but I love using it because it works in
it's a good
favor.
place to start, right? And do you think we have, I mean, I guess our resolution is good enough that we're seeing that deformation. It's not like, is there any deformation that could be happening below our resolution to detect it? I mean, there's got to be,
Sure.
right? Just like there's tinier
Yeah.
earthquakes than what we can measure, I suppose, right?
Exactly.
Okay.
But a lot for a long time, volcano monitoring was guided by seismology. When you saw earthquakes, then you went and you started looking for other things. Now we have these, deformation cameras in space, and we can use INSAR to look at places. You don't have to go there with all your instrumentation and invest huge amounts of time and energy into taking a measurement. You get it kind of from space, and you can process the data on your computer in your office.
Right.
And that's how things like the South Sister deformation were discovered. There were no earthquakes that made people run to South Sister and look for inflation of the ground. It was discovered by looking at these
That the
different
deformation.
satellite images.
Yeah.
It still does guide us, the seismicity. So an example is Edgecombe in Alaska. It's sort of in the southeast part of Alaska near Sitka. There were some earthquakes there. And so, all right, maybe we should look at this. And when you look at the INSAR, the interferometry, you can see, well, the thing had been inflating actually for a couple of years before the earthquake started.
Right.
So
It's a
having that
Yeah, go ahead.
that satellite capability is really key in order to be able to look at places where you don't maybe have instrumentation because they're really remote, or you don't have the resources to put GPSs on every single mountain peak.
Well, I'm not a geophysicist, but you got me on board the deformation thing, because as a structural geologist, thinking about like the rheology of the rocks, you need the right conditions in order to break the material. And so I kind of go back to what we've seen a little bit in Iceland. And this was just my speculation, but I swear I read something about this, so it wasn't just out of thin air. And that is when you have magma that's now cooled off. It's not solidified yet. It is not rock yet, but it is no longer magma. There is this sort of gray zone where the material is not brittle enough to break and generate earthquakes, but it's also somewhat resistant. It's not going to flow as it might move a little bit, but it's not going to flow as well. Because we were thinking about how, future, maybe the magma can't actually move into that zone where that somewhat stiffened magma is, because it has this different rheology in between, and you literally can't break that material because it's just not brittle enough.
Yeah, and there's all kinds of weird rheologies that are happening beneath the surface. There may be no earthquakes because the area is too hot and too ductile to support earthquakes, but that can still deform.
Right.
So there's a lot of interesting, ways to use that kind of information to understand the properties of the subsurface. I tend to enjoy interpreting things that are favorable in terms of deformation because
you have a bias.
I like to needle my colleagues.
Right. So do you think the South Sister then has that issue where maybe the rock's rheology isn't conducive to earthquakes and seismic events happening, and yet there's still deformation happening?
That, and there have been some earthquakes. There was an earthquake swarm, if you want to call it that, in like 2004. There were, a few dozen earthquakes, and there were some more recently as well. That's really a sign of the rock being sufficiently stressed that it breaks. And so you have to have the right conditions. It's obviously not too ductile. And then the rate of change has to be enough that the stress
the strain rate, yeah,
the breakage.
Yeah.
So, the conditions have to be sort of right for non-seismic deformation and that eventually becomes seismic. That tells you maybe have reached some sort of, the rocks reach some sort of threshold.
Right. Interesting. This is so great. I just feel like I'm sure everyone's enjoying just the Mike Poland lecture hour. You should just do one of these every day after your lunch hour, or not every day, every week or something, or once a month or whatever. Well, I want to make
a
sure
lot of people from being seismologists to being deformation folks,
yeah,
right?
exactly. Just have your little soapbox that you're promoting your point of view from. Well, I want to make sure we have time for the viewers to ask questions. I guess
Sure.
The last one I want to ask that's important to me. I know we didn't get to Yellowstone, and I know there's always fun things happening in Yellowstone. Maybe someone will ask a question, but I'd like to really know at Kilauea, you were just there, and I'm really interested in what's been going on there since December 23rd. As many of the viewers know, we just finished, I think, episode 18. Just wrapped up yesterday, I believe, and there's been these cyclical episodes in the summit from these sort of twin vents side by side, and there's been a very predictable pattern of behavior for the most part, where there's been inflation, and then there's been some gas pistoning or some other behavior, and then the fountaining. Like, maybe explain what's happening there, and then also like how that's ever going to change. Like what would cause that to like should we expect that for the rest of 2025, or is it kind of back to this question of, well, a magnitude 4 earthquake will just change everything? And
I mean, we don't know what's going to change everything. It's so what's happening here is the volcanic system has settled into a pattern where you've got a well-established conduit system from the magmatic storage area to the surface. It's sort of percolating there at a low level between episodes, and you could see glow and so forth.
So it's just below the surface.
Yeah. And gets these fountains going in the gas pistoning is you're getting a lot of fresh gas charged magma into the system. And you can see that in the inflation of the volcano as it's filling up, it's pressurizing. When that gas rich magma finally gets to the vent, it starts with some pistoning or starts with some flow out, and then you get the fountains. And that's when you're sending off, you're getting rid of all of that gas. You've shaken up the soda and you've opened the soda bottle.
I mean, it's almost geyser-like in a way. Is that a decent analogy? Yeah.
And then the degassed magma sort of settles back down, and you've got this denser gas poor magma now that's sort of sitting on top, and it drains back in. And it takes some time for the gas to come back in and recharge the magmatic system, and then you go to the next fountain. And this, while not completely unique, is special because these kinds of fountains have only happened a few times. At the summit, you had to go back to 1959 to see these high fountains like this. They also happened during the Mauna Ulu eruption, which was late 60s, early 70s. And then from 1983 to 1986, out on the East Rift Zone at Pu'uo'o, there were 46, 47, 48, something like that, fountaining events there. And they look the same in that the summit area, even out in the East Rift Zone, the summit area would deflate when the fountain was happening, and then you'd have this period of recharge where everything sort of repressurized, and then the fountains happen again. Pu'uo'o went 3 years of fountains. Kilauea Iki in 1959 went a month. So I think we don't have a really good sense of what controls when these things start and stop. We don't know. I mean, episode 18 didn't really have a high fountaining episode. So are we seeing maybe the end of this? It's difficult to know. This is one of those problems with understanding the physics of what's going on inside the magma chamber. We don't know enough to be able to really say exactly why it happens the way it does and how long it may last.
But the whole thing's been driven more or less by fresh, gas-rich magma working its way to the surface, but then not having enough pressure to sustain that for long periods of time. And so that's why you get it kind of dying down. The gas poor magma kind of lava kind of like puts a cap on it for a while it repressurizes from beneath, and then you get another episode after that.
And I think there are going to be some fascinating research results that come out of this event, because the geologists at the Hawaiian Volcano Observatory are collecting samples from episode to episode, and you can look at the composition of little inclusions of melt in the crystals that are being erupted. And that tells you something about the conditions in the magma chamber, especially with respect to the gas pressure that's present and the composition. So I think what's going to come out of this is some really spectacular research results about the conditions in the magma chamber during this episode of high fountaining at Kilauea, and how it varied over time.
Right.
There's going to be some really cool research that we get in the next few years out of this.
And some of those crystals will actually be recording their movements, maybe up into the system, didn't quite erupt, and then maybe they move back down, and then they move back up. And so you'll be able to see like their position relatively like in the crust from deeper levels to shallower levels.
Yeah, you might see the crystals sort of convecting in the magmatic system before they finally erupt.
Right.
Some of that was seen with the lava lake that was present in 08 to 18. That there would be some crystals that had these sort of resorption textures. It looks like they were growing, and then they were getting dissolved, and they were growing as they moved around in the system before finally erupting.
Getting recycled.
I mean, there's going to be so much that can be learned from this. The data sets that are available now, compared to what was present in 1959 or even 1983, 86.
Right.
I mean, night and day, right? We're going to be able to see this kind of eruption with all kinds of different geophysical tools, geological tools, gas emission measurements that weren't even possible, the last time this kind of activity happened. It's an exciting time to be a volcanologist in Hawaii.
Yeah, and you just never know. We still just don't have a handle on the architecture of the plumbing system. I mean, despite all the cool tools we have maybe some ideas, but we really don't have the details of like all the levels, how the interconnections between those magma systems, where it goes off to the east rift zone, where it can go into the southwest rift zone. And so it's just, I don't know. I wish there was a better way to understand like how it's all connected, and why can't you, a lot of people envision it. Some of my viewers have asked like, well, is it kind of like an ant farm? And at least in Iceland, I think that's true because it's a new system. You start out with just whatever fractures and structures are there, and that magma injects itself into, subvertical conduits and maybe some subhorizontal conduits. I think something like Kilauea, it's probably more of a blob, maybe, but it probably has, in detail, it probably has more, geometry and detail than that.
Yeah, and there's going to be all kind of weird offshoots and places that are mostly cool or mostly molten, and it gets into some kind of fundamental questions like, what's a magma chamber? At what point does it become?
That's why I kind of quit using that. As just a magma storage zone sounds more like generic than a magma chamber. I always think of like the big blob, which we all draw in lectures and stuff. Yeah, but it's probably not as accurate. So wait and see in Hawaii is what you're saying. Just enjoy the show, and we'll see what we get next.
Yeah. Well, it'll be interesting to see how the volcano adapts from this episode 18 that didn't have that high fountaining phase, at least not to this point.
Right. Yeah. Great. Okay. Well, I should probably stop hogging the show with Mike, and let's go to the viewers. Looks like I got a page here. Thanks, Amanda Joe, for sending these. So I'll just hit you with these questions here, Mike, if you're good. And
sure.
So thanks to all the viewers for sending those, and we'll do as many as we can here, maybe another 40 minutes or so if Mike's okay. Okay, the first one is from Amanda Joe, our great friend in Iceland, that wants to know where you got your sweatshirt, where she can get one.
Yellowstone.
Yeah.
I can't remember what one of the stores in the park, but the reason I got it was because it had a tag on it that said, "Did you know that Yellowstone has around 2,000 earthquakes every year, and that these are related?" And I thought, my goodness, they're putting geophysical information on a sweatshirt. I'm there.
Right. If
only it was only about earthquakes. They didn't talk about deformation.
That's what I was about to say. If only it was like a little price tag with an interferogram on it, and you would have bought 10 of those. Yeah.
Oh yeah, they would. That would have been
right.
That would have been unfair.
Send me a case. Okay, so yeah, and Amanda Joe, I think you can get it through. What's the nonprofit that runs all the
Yellowstone Forever?
Yellowstone Forever is the nonprofit. And they have an online store, Amanda Joe, and you can get one sent to your house. So. So these were some questions just sent before we actually got together today, Mike. But the first one here, I think these are pretty rapid fire. But how often do volcanic eruptions occur at Yellowstone?
Not often. The last one in Yellowstone National Park was 70,000 years ago. It was a lava flow that created this the Pitchstone Plateau in the south part of the park. Most of the eruptions in the last 600,000 years have been lava flows, and they are episodic in that you'll have half dozen or so eruptions. Maybe they're happening coincidentally. They're almost certainly happening within a few hundred years of each other. And then you'll have thousands to tens of thousands of years of quiet. and then there's another spate of eruptions, and then period of quiet, and another spate of, so you get these very episodic kinds of things. And we're in one of these periods now of quiet. When it will end, we don't know. But more and more people have looked at the status of the magmatic system beneath Yellowstone. And no matter whether you look at it with seismic or electromagnetic data or whatever, it's just coming out as mostly solid and stagnant. So
Yeah.
it doesn't really look like it's capable of supporting an eruption at this point. It would have to kind of rejuvenate itself to a significant
Which could
degree.
take a long time. It could take thousands of years. Who knows, right?
Yeah, yeah. So it's just not something, an eruption, given the conditions of the magmatic system in Yellowstone now, is unlikely. That's why the hazards we focus on there are strong earthquakes, something like the magnitude 7.3 that occurred in 1959. That was a tectonic earthquake. Or a steam explosion, like the one that happened back in July at Biscuit Basin.
Right. Those are the more likely events. Okay. Was the big Yellowstone eruption the biggest in the world?
No. The biggest Yellowstone eruption was the Huckleberry Ridge Tuff eruption that was about 2.1 million years ago, and it created a caldera that sort of spanned, it came into about where the lake is, and it goes all the way out into the Island Park area of southeastern Idaho. That eruption still was about half the size of the eruption that occurred at Toba 76,000 years ago. That's in Indonesia. That's probably the largest eruption that is known. There's uncertainty, and there was some big eruptions in Colorado about 25, 26 million years ago.
Yeah, and Utah also, those
Wawa Springs and La Garita caldera, Fish Canyon Tuff.
Yeah.
But the Toba eruption might be bigger than all of them. And that was only 76,000 years ago. That was a big eruption.
Right.
But it's really difficult to calculate the volumes of these things because the deposits are spread all over the place.
Right. And the older ones even more so because they've been dismembered by faults and moved all around, and then you got to put it all back together, and it's tricky. So
yeah, so I'd say like that Huckleberry Ridge eruption might be the lower part of might be top 10, maybe.
Yeah.
Maybe it even falls outside the top 10. The most recent Yellowstone caldera eruption probably wouldn't even be top 20, top 25. It's I'm not trying to make it sound small, but there were much bigger ones.
Yeah, they're all big, but there's some that are bigger. All right, why hasn't Yellowstone had more eruptions if there's a hotspot there?
Well, the Yellowstone, so Hawaii and Yellowstone are both hotspots, right? And Hawaii goes nuts, and Yellowstone has these very long periods with no eruptions. And that's more than likely a result of the setting. So in Hawaii, you've got this very thin crust. It's a pretty dense crust, this oceanic crust. And so the magma can rise through it pretty easily because the crust is pretty dense and the magma just shoots right through it. The opposite is the case at Yellowstone, where you've got a lot of continental crust. It's very thick and it's not particularly dense. And so magma stalls on the way up. It's harder to get it to erupt. That also affects the composition because the magma spends a lot more time sitting around in the crust, and it can pick up some of the crustal rock, and it also sits there and differentiates. So you're more likely to get a higher silica eruption. That's why you get more explosive eruption in these really thick lava flows in Yellowstone. But it's really the nature of the crust that it's transiting. You build this really big magmatic system, but you don't have frequent eruptions just because of the nature of the crust under which the system is sitting.
Right. So just, way more magma in the deep down associated with that hot spot. And a lot of it's just hot rock. It's not even actually magma yet. So, right.
Yeah, exactly.
Okay. Let's see. What's the most unique geologic feature of Yellowstone? Another subjective question, but
I mean, it's funny because I could go towards like the coolest things, which there's some really amazing formations and places where you can see, some of the ash flow tuffs from the 2.1 million year old caldera plastered up against rocks from the Cretaceous.
Yeah.
And so there's clearly a bunch of time
Mount Everett,
missing.
yeah.
Yeah, exactly. That's a cool feature, but that's kind of a nerdy geologic feature, right? The most unique feature I think has to be the geysers.
Mm-hmm.
There are more geysers in Yellowstone than any place on Earth. About half the world's geysers are in Yellowstone. The conditions that you need to get geysers, well, you need first a lot of water. Well, the Yellowstone Plateau is the highest area on average in the Rocky Mountains, and it gets a lot of precipitation, a lot of snow. So you've got the water source. You need heat. Well, We've got that thanks to the magmatic system down there. And you need the geologic conditions that are conducive to the formation of all these conduits and reservoirs for the hot water to move through. And the rhyolite volcanism provides that. The ash flow tuffs, the lava flows, that's a right kind of geologic conditions to forming those conduits. So you've got everything is sort of perfectly aligned in Yellowstone for geysers. You get geysers in other places, New Zealand, Kamchatka, California, Nevada, but the conditions are so good in Yellowstone that you get more geysers there than any other place in the world.
And your heat source is really big. So you have a really broad source of heat as opposed to maybe like a little stratovolcano or something, which is much smaller in diameter.
Yeah, the heat source, there are other big heat sources in like the Taupo region in New Zealand is a huge heat source.
Another
There's many big
caldera,
caldera
right?
systems in New Zealand. But the conditions are just perfect in Yellowstone for really having a lot of these features, a lot of the geysers and hot springs. And the chemistry of these things is pretty diverse too, thanks to all of the different environments that you have in Yellowstone.
Right. Yeah, excellent. Okay, from Heidi, are there any, so now these are people on the live chat, so are they using other satellite or remote sensing methods except other than NSAR and GPS? Like what other tools are used?
Oh man, there's so many cool things you can do from space. I mean, high resolution visible by itself is neat because you can, see. We use that to detect the explosion that occurred in April of 2024 at Norris Geyser Basin. There was a hydrothermal explosion. We could get a sense of when it happened based on some infrasound data. That's acoustic data that we were recording. But you could also see changes in the thermal features based on high-resolution optical data sets.
So you could just see the debris scattered out the next day kind of thing?
Not so much the debris in that case, but you could definitely see that some of the nearby features, some of the nearby hot springs had drained away rather suddenly. Well, that's probably a sign that something kind of weird happened, and sure enough, that correlates in time with when the acoustic signal occurred. So the high-resolution optical is by itself pretty neat. We can measure gases from space. Most of that is by using ultraviolet spectroscopy, basically. You can also use infrared. You can measure thermal emissions from space. So you can get a sense of whether or not a volcano may be heating up or cooling down. So there's a lot of different parameters. Looking for ash plumes, which is increasingly important with, you got air traffic going over volcanic areas. You want to be able to detect dangerous ash plumes, know what altitude they're at in real time. And weather satellites can do that to a large degree. So you can see just about everything to some degree from space. The only thing we can't do from space is seismology.
Right, is see into the ground, right?
I'll throw my seismologist colleagues a bone.
Right.
We still do need a lot of seismic stations on the ground to get good earthquake locations for those tiny events.
Because everything satellite or above Earth based is still superficial data. Is that true for the most part? It's gas emissions, it's ground changes
in the atmosphere,
So interesting. Okay, from Grumpy Frank, my question might be a little loaded. Something like, do you use and can you explain SOACOM INSAR, SAOCOM INSAR, and how best to read it and use the data alongside the smaller wavelength satellites like Sentinel-1?
So SOACOM is an Argentinian system. We do use that, and the Argentinian system is a longer wavelength than Sentinel, or much longer than TerraSAR, the German system. The longer wavelength is more capable of penetrating vegetation. So in some places, that L band, that longer wavelength, allows you to see through trees. So for example, at Kilauea, along the East Rift Zone, where there's rainforest everywhere, you get slightly better signal return using data from a satellite like SOACOM than you would from Sentinel, TerraSAR-X, or Cosmos SkyMed. There's a Japanese system called the ALOS-1, ALOS-2, that also had an L-band radar that was very good at seeing through vegetation. In some places, it was like, with the shorter wavelengths, you just couldn't see that much because the volcano is so vegetated. With a longer wavelength, it was like turning the light on in a dark room. You could see everything.
Right.
So it's not a cure-all because it doesn't see through everything, but it sees through a lot. And there is a new joint US-Indian system that is on the verge of being launched, hopefully sometime in the next few months, that will also be L-band so longer wavelength, and it's going to be hopefully providing worldwide data over faulting areas and volcanoes that we're also going to be able to use pretty reliably. So SAOCOM is part of this system of satellites that we can use that have different capabilities. And it's been pretty useful in Hawaii.
So are they moving towards the longer wavelengths? I mean, it feels like you just sold everyone on longer wavelengths, but there's got to be a downside to it. Like otherwise everyone would switch to it.
Yeah. Oftentimes the longer wavelengths, you're looking at broad areas and you can't see small deformation as clearly, and you can't see localized deformation as clearly.
Right.
So there's no perfect system. You can maybe think of it as having a camera with a certain filter on it that's set to the broadest view possible,
right,
versus a camera with a really amazing zoom with a different kind of filter on it that can really see something that's a very fine scale that might be missed by the broader view. So it's one of these, like if you're going to go to a construction site, you don't just go with a slot screwdriver, right?
Right. You bring all your tools, yeah.
Yeah, you have different sizes of them because maybe you've got a micro screw versus a giant bolt. They all have their uses. None of them is perfect, but when you use them in combination, you basically get a pretty synoptic view of what might be happening.
A nice comprehensive tool bag. Well, I'd never heard of SAOCOM. That was good for me to learn. All right, from Susan Smart, she's asking you, were you able to install equipment near Biscuit Basin?
That is hopefully going to be happening soon. We haven't been able to do anything yet because it's still basically winter in Yellowstone, but that's on the docket for this summer. And I'll be headed out there in early May, meeting up with some colleagues there. We're going to try to figure out where the best places would be for another acoustic monitoring system that would go in the Biscuit Basin area. There's some, we got to find the right place for it. So we can't just say we're going to plop it right down in
next to the boardwalk.
Wherever. Yeah. And so we're going to be scouting out locations that we can put seismic and acoustic monitoring in Biscuit Basin, hopefully next month.
What's the ideal conditions? Is it distance? Is it line of sight without trees in the way?
It's funny because every instrument needs a different thing. So for the acoustics, you want to be able to put them kind of in clumps of trees, because the trees act as a natural wind filter. If you put it out exposed and there's a lot of wind, it just becomes, it's like putting a microphone in a windstorm. All you hear is the wind. For the GPS, you don't want trees anywhere near you, and you want really solid rock, right? So you can anchor a GPS station in solid rock with a great sky view. And for a seismometer, you want to be able to dig into the ground so you can bury the seismometer, because it's ideal to have these things sort of in covered areas to keep them a little bit quieter, so you're insulating it from the surface noise. So you need a place with trees, but not too many, with solid rock, next to a place where you can dig a small pit for a seismometer.
It's Goldilocks, right?
Right. And so chances are we'll find, 2 of the 3 conditions we need. And so maybe we'll put the acoustic and the seismic sensor here, and the GPS will have to go over here, or something like that.
Because you want them all to have the same telemetry and share a power source, and yeah.
I mean, ideally, if we can get them all in the same place, then you've got sort of one hub for telemetry and power.
Right.
If you put them widely separated, then you need to have a lot more equipment, and we're trying to minimize the footprint, trying to minimize the impact of any installations.
Right. Interesting. Okay. From Cassandra Weeble, have there been any high magnitude / major earthquakes this month? I'm assuming she's talking about Yellowstone, so you can take that however you want.
Yellowstone has been remarkably quiet in terms of seismic activity for months and months and months and months. There really just hasn't been much of anything. It's really on the low end of average for the past, year and a half, earthquake wise.
Mm-hmm.
I think the largest earthquake last year was like a 3.1 or something like that. It wasn't very big. In fact, it was in January of 24 that the largest earthquake in 24 happened. And I'm not even sure I think we had 1.3 maybe so far this year. So everything's been very low level in Yellowstone lately.
Right.
I mean, it ebbs and flows, and we're in one of the ebbing periods right now.
Just a little slower now than it normally is.
Now that I've said that, there'll be an earthquake storm tomorrow with 200 events or something like that.
Yeah, there'll be like a 3.8 and a 4.5 or who knows, right? Yeah. Ken Wilson wants you to talk about recent high-resolution tomography project in Yellowstone.
There have been so many cool results. with respect to Yellowstone's tomography. So back in 2020, this is one of the only field experiments that happened in big ones that happened in 2020 because of the pandemic. University of Utah, University of New Mexico, several scientists got together and they deployed 600 temporary seismometers all across Yellowstone region. And those seismometers recorded natural earthquake sources that were happening all over the world, right? And you get the signals coming through Yellowstone. They also drove a vibroseis truck, which is a truck that kind of shakes the ground all around Yellowstone. And by creating seismic energy at set locations, they sort of knew all of the characteristics of the earthquakes, essentially, they were creating, where they were happening, the frequency of the energy that was being generated, and so forth. Especially that active source one generated by the truck. The waves would go down and then they would bounce off the top of the magma reservoir and then come back and be recorded by the seismometers. And that has suggested that there is sort of a volatile rich, that's sort of a gassy rich top to the Yellowstone magma reservoir. So there's sort of a top part of it that's low density and has a lot of the gases that then feed into all of the hydrothermal system that help keep that going. One thing that all of these studies have said, whether you're using the regional earthquakes to look at how natural earthquakes travel through the Yellowstone system, whether you're looking at the active source, whether you're looking at the electromagnetic characteristics of the subsurface, is that the magma chamber is mostly solid.
Right.
There's just not that much melt in the system. It appears to be stored in little lenses, the melt that's there, and little sills that are sort of interspersed with one another, but there's no big molten collection of material beneath Yellowstone at this time.
Interesting. So just another sort of line of evidence that suggests that, in addition to
and they're all, that's one thing that I found interesting, is all these different studies are using different data types, or they're processing the data in different ways. Some look at past data, some looking at most recent data collected, seismic, electromagnetic, whatever. They're all sort of converging on the same result, which I think is cool.
It's mostly
right?
crystal mush. Yeah,
I mean, it's reassuring, but it also is telling a story, and you got to love it when the data all start to come together into a story that fits everything. I mean, that's ultimately, we know we're dealing with the same system and we're looking at it from different directions. And so you want to be able to come up with a story that satisfies all the data sets, and that's what's coming together. And that's really cool. That's really satisfying.
Interesting. Were they able to use that to figure out like what percentage? I know there was one study several years ago that said, I don't know, you'll remember the number, like 70% or whatever of that magma volume has turned to crystals or something like that.
Yeah, it varies. Like, it's probably a little bit, in the 20-25% level in these little sills or whatnot, and then it's, zero in some of the other areas.
Right.
So it's really been neat seeing over the last, especially decade, the increase in resolution. It's like having a digital camera that, it was 1 megapixel and then it was 10 megapixel. Now it's 20 megapixel, and that you can really start to see what this thing looks like. It's not just an amorphous blob anymore.
Right. It's starting to have like more defined characteristics to it.
Are
you good for like 8 more questions? Is that okay?
Yeah.
Okay.
Bring them on.
All right. From Keaton Terry. Hi again, Mike. Just like last time, I'm asking a question about the Yellowstone Snake River Plain. Why is craters of the moon polygenetic when all other young basaltic volcanoes in the Snake River Plain are monogenetic?
So I guess I would not use the term polygenetic for craters of the moon, because we generally say polygenetic, which means we assign that to a specific eruptive feature. So a volcano that erupts from the same vent system, from the same magmatic system many, many times. Mount St. Helens is polygenetic, whereas Sunset Crater is monogenetic. It has a single eruption and then it's done. But craters of the moon is sort of there's a locus of activity there. There are a lot of repeated eruptions. It isn't necessarily building a polygenetic volcano that we keep seeing eruptions from the same volcano, but we are seeing eruptions more in this area than in other areas of the Snake River Plain. There's a lot of potential reasons for that, but one is sort of the tectonic situation creates more extension in that area than in other areas. And so that extension sort of facilitates upwelling of magma and decompression melting. And so you're more likely to get magma generated in that area than you are in some other areas of the Snake River Plain. So the odds are more likely you're going to have one of these one-off eruptions happening in craters of the moon
Right.
than in other places of the Snake River Plain. There are some polygenetic volcanoes in the Snake River Plain. There's a shield volcano that the name is escaping me right now. I feel like it begins with a P, but
Where's it
there
at?
are a few places.
Like which?
Oh, I'm gonna have to look that up.
Eastern Idaho or closer to craters, or
I think it's off to the northeast of Craters of the Moon, I think. But
it starts with a P. Is it out by Big Southern Butte or anyway?
No, it's not. It's not one of those big rhyolite things.
Well, there's a couple near Big Southern Butte that are some good sized
I think it's not far from Big Southern. But
what's the evidence it's I mean, what I'm interested, as a piggyback question, how do they determine with some of these older ones that they're, at what point do you decide it's polygenetic? If it starts erupting, and I mean, look at Hawaii as an example. We're calling this all one big phase from December 23rd on, but it's stopping and starting and stopping and starting. So how much of a quiescent period do you say, okay, that's over, and then if you get another one, that's a separate eruption versus part of the same system?
That's a good question, right? I mean, somebody somewhere has to sort of decide, all right, well, enough time has passed to call it a new eruption. In the case of this thing in Idaho, I'm pretty sure the results are from geochronology, some are from Paleomag, where you can see that there were significant time gaps. Now, what those time gaps are, I can't recall off the top of my head right now.
Right.
I feel a bit silly for even not being able to remember it, because I was just reviewing some articles that discussed this, but it was long enough ago, a few months ago, that I've forgotten the details.
And you're the scientist in charge of an observatory that not only handles Yellowstone, but all of the Snake River Plain, which is a lot of vents. So I'll give you a pass on that. That's a lot of volcanoes to keep track of.
There's like 600 vents on the Snake River Plain. It's a big system.
It's pretty crazy. So, that was a good question from Keaton. Foxfur wants to know, will the movement in Hawaii eventually result in a slide into the ocean?
Debatable. There has not been a catastrophic slide on that side of the volcano. It may be that it's just a slow slump and that's all it ever becomes.
Yep.
The Hawaiian Islands, we see evidence of both of these sorts of things, where there were obviously very slow slumps that just gradually, gravitationally carried bits away. Never was a catastrophic failure. There's other places where you can see really, truly catastrophic failures. The other side of the island of Hawaii, Mauna Loa, collapsed catastrophically a couple of times. That's why some of the topography over there is so steep.
Mm-hmm.
Anyone that's driven from Kona down to South Point has gone through 15 miles of really unpleasant curves.
Right.
And that's because that area is quite steep, because there was a catastrophic slide there. I can't remember what the timing was, but 100, 200,000 years ago, something like that. So we don't know whether the south flank will catastrophic fail at any point, but the signs sort of suggest that it won't, because it's just sort of this slow slump, and it has never shown signs of a failure over the 100, 200,000 years of Kilauea's history. So it's just sort of an active creeping slide. Yeah,
hard to project what it's going to do if it's going to keep doing that.
But this is a common thing. I mean, every time there's an earthquake at Kilauea, this lights up social media, right? Look, here goes, the whole thing's going to collapse. There'll be a tsunami that destroys California. And well, no.
the tendency to just go to the extreme is higher than it's ever been among the masses. That's for sure. Elaine Jones from Tucson wants to know, do you have to request time on an INSAR satellite to study an area for deformation?
Sort of. So some of the satellites allow us to put in a tasking request. So we'll say, we're really interested in this volcano or this place. And we're kind of in competition with other people, because the satellite, it can view different things from where it is. And it might be that, in some places you want to look at a fault, or if you tilt the satellite a different way, you're looking at an area of ground subsidence, or tilt it still further, you're looking at a volcano. So there's some competition for tasking. A satellite like Sentinel, it's just always on, and it's always collecting data. Something like TerraSAR or Cosmos SkyMed, you kind of need to request that an area be acquired. And there's ways to do that. You can submit requests online or send them to colleagues. And
do you specify the angle and stuff too? Like, we would specifically want a pass looking, at this azimuth or whatever. And
right.
Okay.
Yeah, and so you would know, like, all right, if I want to get an image of, you know, craters of the moon, there are certain options, and I'll pick the options I think are going to give me the best viewing geometry.
Right.
But it might be that somebody else is looking at, I don't know, somebody else is trying to look at something else in Idaho that's at a slightly different angle, but would use the same point in space. And maybe they have a higher priority than I do for whatever reason, or maybe I have a high priority than they do. So there's some competition for tasking, but usually there's enough views that you can kind of get what it is you're looking for. And it's not just looking this way, but you can look that way too.
Yeah.
So
Right.
there's kind of something for everyone. But oftentimes, yes, for some of the specialized satellites, you need to request that the data be acquired.
Right. So they see Mike Poland's order on the task sheet and they're like, well, we got to fulfill that.
Yeah.
Like,
No, they're
no,
like,
it's the
yeah.
other way. They're like, let's go to something else.
But then these missions like Sentinel or NISAR, the U.S. Indian mission that's going to be launched soon, they're designed to be always on and always catching things.
Right.
So some of them you don't have to make the request because the
It's coming anyway.
Get the data.
Yeah. You just got to wait for the next pass or whatever. Yeah.
Right. Exactly.
Okay. David Newton wants to know, what is the biggest threat from the less active volcanoes Hualalai, Mauna Kea, and Haleakala?
So these are, Haleakala is Maui, and then you've got Mauna Kea and Hualalai on Big Island. Hualalai is an interesting one because it sort of looms over Kona and the Kona coast. It is still pretty active. It last had an eruption in the very early 1800s. So that is an interesting one. I think in a lot of other places that volcano might get more attention, but it's on the same island as Mauna Loa and Kilauea.
It's like third banana.
Yeah, it gets kind of overshadowed. Mauna Kea is much less active, and there's less for it to damage. Obviously the telescopes, but those are all at the summit. And Mauna Kea is at this stage of life where an eruption could happen sort of anywhere on the mountain.
Yeah.
You look at the mountain, there's bumps all over the place. There's cinder cones all over the place because of these vents that just sort of form, kind of anywhere on the mountain. Last one occurred 4,600 years ago, I think.
Right.
Haleakala is a little bit more active. It's probably on par with Hualalai. The last eruption there, I think, was in the 1500s. So yeah, Hualalai is kind of a sleeper for.
That's what I would say too. Yeah. Yeah, I think last time I was there with people, I don't know, I had a tangent where I was comparing them all to like people, and I think I told the Mauna Kea was kind of like the elderly person on hospice, like, still there, still kicking, but like, its time is, it's mostly gone. And Hualalai is, Kohala, it's like 6 feet under, it's done.
Oh yeah.
But Hualalai is maybe, it's like person in like me or you, like in their late 40s, early 50s, like we still have some time. We could still do some things. And then you have Mauna Loa, which is 25-year-old vibrant in its prime, and then the restless teenager Kilauea is like maybe the 16-year-old that's starting to feel their oats a little bit. I don't know.
Yeah, I think and in the USGS ranking for volcanoes, Hualalai is considered a reasonably high threat.
Yeah.
And it's got monitoring on it, because there is a concern, right? That we knew it erupted in 1800 and 1801. It will erupt again. The timescales are unknown because it's in that sort of later stage in its life where it's a bit more random than something like Mauna Loa or Kilauea.
Wouldn't you agree, though? It potentially would have more impact on more people than Kilauea, just by location and proximity to like towns and stuff, like the whole Kona coast versus just the Puna area.
I mean, it depends, because that 1801 lava flow, I mean, the Kona airport is on that lava flow.
Right.
So obviously it could have a pretty significant impact on some infrastructure, but it sort of depends on which way it goes.
Yeah.
But, I mean, the same is true of Kilauea.
There's just more in its shadow than like Kilauea doesn't have a whole lot of a human footprint on it or near it. I mean, as much anyway.
Right in like the southwest side, certainly. Yeah. But there's the other concern perhaps for Hualalai is that there hasn't been an eruption in 200 years, more than that. So there's not a memory, and of course that can breed a bit of complacency. Yeah. So that's something that as volcanologists you can't accept that.
Yeah.
You have to be just as aware of the one that hasn't erupted in 200 years as the one that is erupting right now.
Yeah. No, that's an interesting perspective. All right, question about Yellowstone from Quake Cat, Utah. Does Yellowstone and other volcanoes in a way, quote, breathe? So the volcanoes like Yellowstone
Yeah.
breathe in a way.
Yeah, they do. Yellowstone, the deformation, sometimes it's inflating, sometimes it's deflating. And Yellowstone, I think more than most caldera systems, has this really nice pattern of up and down. Typically, it's at rates of an inch or two a year. It has been uplifting. Sorry, it's been subsiding since 2015. But then it had a period of uplift from 2014 to 2015. From '09 to 14, it was going down. From '04 to '09, it was going up. So yeah, it does sort of breathe. I think
Right.
that's an interesting way of putting it.
Yeah, just inflation deflation cycles, kind of similar. Chip Hall, recently in the news, there's been new information about the Yellowstone magma chamber. Is there any truth to this new information? But they didn't
Yeah,
say. Maybe you know what the new information is. I don't know what they're talking about.
well, this is what I was referring to with the new active seismic experiment that we
Okay,
talked about a little
with the
bit ago, and seeing this
crystallization, yeah.
volatile rich cap that exists at the upper limit of the reservoir, and that comes from this big deployment of seismometers and running the truck around Yellowstone in 2020. So yeah, there's a Nature article. In fact, I think I have it.
Oh
I have
yeah.
it right here. This Nature article that is all about the new
Oh, okay.
results from the Yellowstone system. It was just published less than a week ago. So it's interesting stuff, and it's an amazing new view of the system that's coming more into focus.
Right.
The one thing that has become sort of a joke among some of my colleagues is that it doesn't matter what the research result is. The second part of the headline about it is always sparking fears of an eruption, or something like that.
Volatile.
Yeah.
It has the word volatile. Volatile
Right.
cap.
Sparking fears of eruption.
Right.
And yet, when you read it, it says right in the abstract, we infer the magma reservoir is in a stable state of efficient bubble ascent, and the basis of that estimate is a crystal-rich reservoir for which modeling favors bubble escape that prevents instability. That's a lot of blah 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 to basically say it's stable.
Yeah. Right.
Right. And so right there in the very beginning of the paper, they talk about how the point of this research is not to say that it's about to erupt at all, but
someone will twist it. Someone will spin it. That's the way it works.
Yeah.
Jeez. All right, 3 more, Mike. Then we'll let you go. Skip.
Okay.
Skip says, "Why won't Yellowstone erupt? Is there not too big an answer? Are the geysers some kind of release valve?"
That's a really common perception that the geysers are releasing some pressure, but it's probably not really the case because the two systems are not directly connected. The heat engine is the magmatic system, and that's heating up all of the water, but there's no direct pressure connection. In other words, pressure accumulating in this magma reservoir is not sort of transferred to the hydrothermal system and then released in geyser eruptions. So thinking of them as a pressure release valve is probably not the right way to approach it. You can think of them as an expression of that heat engine. And if you were to see really wholesale changes in geyser activity, it might reflect something going on in the heat engine. For example, a cooling down or a heating up. Of course, there's other factors too. If there's really impressive drought, there's less water and there's going to be fewer eruptions.
Yeah,
We've seen that happen. There was a period where few hundred years ago where Old Faithful seems to have turned off for about 150 years, and that corresponded to a period of really impressive drought in the region. So there's a lot of competing factors, but fundamentally, the heat engine just is not powerful enough to generate so much magma that can overcome this low density crust that the system is sitting within. That probably takes some special conditions. We do see in past eruptions, and looking at the crystals, we can see that there were influxes of heat prior to eruption. So it looks like this magma reservoir probably sits around in this mostly solid state for long periods of time, and then has some sort of injection from beneath. And that jumpstarts things.
Right.
It remelts part of the reservoir, and then you get enough melt generated that you can trigger an eruption or series of eruptions in the case of these episodic lava flows. That's going to be accompanied by really outstanding amounts of change that we'll see at the surface. Seismicity, ground uplift that you'll be able to see with your eyes, changes in thermal emissions and gas emissions. So that we're not seeing any of that now suggests to us that we're in this, stable state where we don't have that injection that's rejuvenating any of the magmatic system. Might happen at some point,
Yeah.
but that still would take a while to get us to a point where we could generate enough eruptible magma.
Right. Excellent. All right, two more from John Falders. So now we're going to Costa Rica, it looks like. Do Poas and Arenal have gas-rich magma?
I don't feel like I'd answer that specifically, because I haven't studied up on those specific systems in that respect. But to an extent, all of these eruptions are kind of gas rich, because gas is the driver for any eruption. It's not momentum, say, of magma that's suddenly shooting up. It's got to be driven by gas exsolution, and the really big eruptions have lots and lots of gas. So it's likely that some of the bigger events that happen in places like Poas, Arenal, or Fuego or whatnot are especially gas-rich batches of magma. But I don't think I could say specifically what their gas contents are relative to other ones. I'd have to leave that to one of my colleagues.
Right. That's a good answer. All right, last question on Hawaii from Charles W53. Is there a source for the gases at Kilauea, or does it go back to planet formation?
Planet formation is really it. I mean, all of the volatiles that are in, well, okay, there's, yeah. I'm wondering how existential to try to get here.
Yeah.
Most of this stuff comes from planet formation, right? I mean, that's ultimately where all of the raw materials come from. There is some degree of recycling that probably happens. So at subduction zones, you're getting some hydrous stuff that's going down back into the earth, and that may eventually come back out again at some point. But the amount of time it takes that recycling to happen is probably very, very long. Whether or not it's having any impact on what's happening at Kilauea, I don't think I could say. There's probably some mantle dynamics people out there that would be screaming right now that it is, or no, it isn't. But that's not me. But fundamentally, it's what we started with is what we still is what's coming out of the.
Yeah, it's all recycled, right? To some degree, just different places.
Yeah, it's sort of crazy to think that all of the stuff that when Earth formed we're still seeing the effects of that, and all those volatiles which came maybe from comets or so forth that were part of the accretion of Earth 4.5 billion years ago. That's pretty cool that's a difficult concept to wrap your brain around.
Well, we kind of wreaked havoc on us from above, and now it's somewhat wreaking havoc on us from below, I guess. So it's just a different thing.
Coming back up.
Yeah. Crazy stuff. Well, hey, thanks so much, Mike. We've taken enough of your time for today, but I know it's always a super big highlight for myself and all the viewers when we get a little bit of your time. Hopefully, again, in a few months, maybe we can circle back. Maybe if you're not too busy with your field season and stuff, we can circle back and just pick your brain a little bit more and learn more about your specialty and volcanoes, and everyone enjoys it. So thanks.
Yeah, maybe in a few months we'll be able to talk about some new monitoring equipment at Yellowstone. That'd be kind of cool.
Okay, yeah, that sounds like a good teaser. So maybe after you get done with your field work there, you can come on and give us an update on what you guys did and worked on. Maybe show us some photos and stuff. That'd be great.
Sure.
Great. Well, thanks so much, Mike. We'll let you go, but thanks so much, buddy. I appreciate it.
Thanks, Shawn.
All right,
take care, everybody. Bye-bye.
Alrighty, so that was our thing with Mike. I can turn my webcam on now. Let's see. All right, let's see. My webcam's being weird, but you guys can probably still hear me there. Yeah, that's probably good. We'll just kind of end it there. Thanks to Susan and Amanda Joe for moderating today. Hopefully we're able to get to most of the questions. We did 2 pages worth of questions, so hopefully that was good for everyone. Mike's always a great guest to have on. Super wealth of information. I just enjoy learning from him and just sucking up as much as I can. So hopefully you guys enjoyed listening to us chat and then also chiming in with your questions as well. Thanks again for everyone for being here. Have a great day. Things to look for in the coming up. I'm going to do some more interviews with some folks. I've got some other interviews in the hopper, another one from Southern Utah and another one from Southern Idaho. I'll get back to doing some more of the Geology 101 videos as well. Kind of in the crazy part of the semester. I've got, 3 weeks to go, finals and projects and field trips and all sorts of chaos, but I think I've got enough stuff to keep this afloat. And we'll look to do another live stream here maybe sometime in May. I leave at the end of May for Iceland and Europe, so let's do something again in May. I'll get together with Amanda Joe and we'll pick something and we'll go from there. So thanks again everyone for jumping on.